So thanks to the organizer for giving me the opportunity to speak about this work that was done very recently, is just accepted and is on the archive since yesterday. I have no time to present all the stuff, and so please, if you are interested, if you are a true lithium lover, you can just read the paper on the archive. The work is done in collaboration within the Gaia-ESO Survey consortium, and you see a list of people who contributed to this work, and some of them are attending this meeting. The goal of the work is an ambitious goal: reconstruct the history of lithium enrichment in our galaxy and establish the establish the various lithium sources and the percentage in which each source contributes to lithium evolution. And you know, this is very complex just because lithium is very easily burned in stars at very low temperatures. So it is very difficult to find out stars that trace the galactic evolution of lithium. And in past time, it was a common practice just to take the upper envelope of the observed lithium versus metallicity distribution. And then people, what's happening now?
Some people have had trouble with going to the next slide.
Yeah, I
not
can.
sure why.
It's completely.
Use your mouse to click in the middle.
Don't know. It's completely blocked. I cannot move. It's just.
If you use the mouse to click instead of arrows,
oh,
it usually
yeah,
works
I'm trying
better.
with the mouse. I'm trying with the mouse.
There it goes.
Yeah. Okay. 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 So another approach, more recent, since you are more data, you can also beam in metallicity, and then you can take the average in metallicity beams. But I think this can be very dangerous because since lithium is easily burned in stars, the risk is that you may show some spurious trend this way. And there is another caveat. And there is a stellar migration in the disk, and these can pollute the trends you are seeing locally. And there is a recent paper by Guillaume, and I am also a co-author on this topic, and you can divide you can divide the population based on the alpha over iron ratios and metallicity, and find out thick, thin disk stars, metal-rich, alpha-rich stars, so on and so forth, and you find different lithium behavior. But here I'm talking about the data set we build based on the last internal data release of the Gaia-ESO Survey and cross-matching with the Gaia early data release tree catalog. And in this way, we can build a catalog containing homogeneous stellar parameters, temperature, gravities, metallicity, and alpha over iron ratios, lithium abundances, and I will show 1D LTE abundances, just because the corrections are quite small for the stars I'm interested in. We checked with Laura the Wong et al. Correction, so it's 0.1 dex at most, so doesn't make a large difference. It doesn't affect the conclusions. And I have unevolved stars. I selected unevolved stars observed with either UVS or giraffe. And we also computed the ages basing on isochrones, essentially, comparison with isochrones. These ages are clearly not precise. And we compute orbital parameters using GALPI. And we build a field star sample. In this case, we combine stars observed in the Gaia-ESO field and also stars that are non-members observed in open cluster fields. And we make a selection based on stellar parameters, remove giant stars, and apply a quality cut, just taking spectra with signal to noise ratio greater than 50. This is good for lithium abundance determination. And we are left with 3,000 to 100 stars, more or less. This is half of the original unevolved star sample. And the reduction is basically due to the cut in signal to noise ratio. And we complement the field star sample with the open cluster sample. We selected 26 open cluster out of 87 for which GES provide abundances and stellar parameters. And we compute the likely undepleted maximum lithium abundance for each of these 26 clusters. These are the results in a graphic form. Starting from top left, you see the kill diagram, and you see that basically many stars are on the cool side of the lithium dip, so they are by sure strongly lithium depleted, and we have only a few stars with relatively high temperatures. So with safer lithium determination, probably tracing the original lithium content of the stars. On the right, you see the sample divided in inner disk, solar vicinity, and outer disk inhabitants. So we have a well-populated solar neighborhood sample, and then a few stars in the inner and the outer disk. And then bottom left, this is the sample for the solar vicinity, and we apply this distinction in different components based on the chemistry on alpha over iron and metallicity. And in red, you have basically thick disk stars, in blue, thin disk, and then you have in magenta the metal-rich alpha-rich stars, and light blue, the metal-rich solar alpha stars. This latest population should not be used for comparison with model prediction in the solar vicinity, because probably they came from different radii due to stellar migration. And the white point are just stars for which we don't have the estimate of the alpha over iron ratio, but we have some hints from kinematics, and these are essentially thin disk stars. And you see that in the metallicity range from 7,000 to 6,000 Kelvin, there are a few stars basically at the meteoritic lithium abundance values. So these are probably undepleted stars. The open cluster sample, we have cluster with ages from very young to relatively old, and we cover a large galactocentric baseline. So we can study with statistical relevance the lithium gradient across the galactic disk, and comparing it with theoretical prediction for the first time. And okay, I have no time to explain in detail how we derive the lithium, the average maximum lithium abundances for the clusters. And I go to the Galactic Chemical Evolution model we use to interpret the data. We adopt the parallel Galactic Chemical Evolution model that has been described just a few minutes ago by Valeria. And so you form the thick and thin disk at the same time out to the distinct episode of gas infall that is assumed to be of primordial chemical composition. So you have a wide overlap in metallicity, distinct sequences in alpha over iron ratio, and also other elements that we showed in a series of papers. And the nucleosynthesis prescriptions, we adopt yields from Paolo Ventura and collaborators for low and intermediate mass stars, including super IGV stars. For core collapse supernovae, we adopt the yields from Limongi and Tieffi, including rotation, but Limongi and Tieffi does not consider the neutrino-induced synthesis of lithium in core collapse supernovae. And so we have to adopt all the yields by Wolseley and Weaver to take account of lithium production in supernovae. Then we have Iwamoto yields for type 1a supernovae, and lithium production from Nova system is taken into account using an empirical yield derived by IDSO. It was the first to observe lithium in a nova spectra, and this came very recently. And we assume that 2% of stars ending their life as white dwarf enter the formation of nova systems. Lithium production from galactic cosmic ray spallation is also taken into account, and with all these ingredients put in our code, we can describe the evolution of lithium in the thick disk. This is the left panel, and in the thin disk, middle panel is in function of, as a function of metallicity, and in the right panel as a function of time. Here, we assume two different primordial lithium abundances, the split plateau value 2.2, or the standard BBGN nucleosynthesis abundance of 2.7. And in one case, we also consider the neutrino-induced nucleosynthesis in core collapse supernovae, just to show you that it is not so so important. The major contributor to lithium, pollution are nova systems, because essentially the yields from single low and intermediate mass stars are very low. So the rise from the primordial value is due to nova systems for the major part. This is the gradient, and you see that both field stars and cluster trace almost the same gradient. Of course, at the outer radii, you have low statistics. It would be really great to enlarge the sample of both clusters and field stars at the outer radii, because there it would be really nice to understand if the gradient flattens out or you may have a steeper gradient. And the model prediction that better agree with the data seem to be the one at 4.5 giga-year ago. So it seems that our model predicts a too steep rise of the lithium abundance with time and metallicity. Come back to the nucleosynthesis prescriptions. So what can be changed in the model to better fit the data? And as I said, the major contributor to lithium are novae. So what we did is to change the mass range and fraction of stars that enter the formation of nova systems. And we have always the constraint that we need to reproduce the current nova outburst rate in the galaxy. So this quantity is not I mean, the nova outburst rate is observed and set a strong constraint for the model. In this way, okay, gray is the fiducial model with white dwarf nova progenitor in the range 1 to 8 solar masses and empirical lithium yields from its et al. Observations, and the fraction of 2% of all white dwarf entering nova systems. And in green, you have the increased fraction, 16% of white dwarf entering nova systems, but the white dwarf nova progenitor have a reduced mass range, 3 to 8 rather than 1 to 8. And we also have to lower the lithium yield from the nova outburst to better fit the meteoritic value, that is the yellow cross in the left panel. And I think in this way, you can better reproduce the upper envelope of the observations as traced by both field stars and open cluster that I remember at lithium abundances homogeneously derived within GES. Of course, we have not so many data. We have some indication, and there is another problem with the data that I will mention here in my conclusion. So I show that we have built a catalog of lithium abundances and high precision stellar parameters alpha over iron ratios from the last data release of the Gaia-ESO survey, also close matching with Gaia data. And we have complemented this catalog of field stars with abundances for open clusters. And we find that open clusters and field stars trace the same lithium story. This is because now we have also hot stars and younger stars than other survey in our sample, similar to GALAH. So this is what Corinne mentioned a few minutes ago. It is important to have hot stars and young stars in the sample. And we find that in general, the abundances, the average maximum lithium abundances in clusters are in agreement with meteoritic abundance of lithium. And this is important because lithium in meteorites is frozen. So there are no destruction processes that can alter the original lithium in meteorites. And our observations are tracing a rather flat lithium abundance gradient across the disk. But I have to mention, as Corinne pointed out in a recent paper, that there may be atomic diffusion effects in metal-rich stars. And so the shape of the gradient can change. In particular, the gradient can be flatter in the inner galaxy. And this is something that is very important to understand. And I think this is up to stellar evolutionary modelers because we need to understand the true shape of the gradient to be able to better constrain lithium production in nova outbursts. And there have been a burst of paper dealing with lithium production in nova in recent years, starting from the detection of lithium in the IDR6 paper, and then beryllium that decays into lithium by Tajitsu, Molaro, Selvelli, other people, and also new hydrodynamical models of the nova outburst by, for instance, the group of Starfield or Hordiose and Denisenkov, and also there have been some criticism about the high lithium yield observed in nova spectra. And the last two, the last paper I list here just say that the nova yield derived from observations is too high, should be lower. So there is a lot of confusion and a lot of room for improvement and to better understand the evolution of lithium in our galaxy. And here I stop. Thank you.
Well, thank you very much, Donatella. Yay. All right, so we could fit in a brief question if someone has something. Simon Campbell.
Hi, thanks for the nice talk. The models for the low mass stars, low and intermediate mass stars, do they include the destruction of lithium on the RGB?
Yes.
The Ventura
yes.
models. So the lithium's destroyed. And so now, well, looking back at Laura's talk, it might be the lithium seems to come back. So need to lithium.
I mean, what I put in as ingredient in the chemical evolution code are the total yields. So they take into account the whole processes of lithium production and destruction in the stars. And so, yeah, it is taken into account. And I do not correct the yield. If they are negative, they are kept negative in the code. So the abundance of lithium can also decrease. And yeah.
All right. Thank you.